Welcome to the E-Pathshala lecture series in computer science. We are dealing with the course computer architecture. So, this unit discusses the fixed point arithmetic unit. So, we will try to look at the various arithmetic operations like multiplication, which we did in the last unit, and continuation of that with division. So, previously we looked at how a multiplier can be implemented using a combinational multiplier and also a sequential multiplication algorithm. Now, the sequential multiplication algorithm can be further speeded up using what is called a Booth's algorithm. So, the idea here is the Booth's algorithm was basically invented for speed, because earlier it was assumed that shifting was faster than addition at that time, and the other objective was to reduce the number of additions required. And fortunately, the main advantage of Booth's algorithm is that it worked for signed numbers as well. Earlier what we decided was, when you have negative numbers, multiplication of negative numbers, you have to look at them as positive numbers, multiply them as usual, and then treat the sign bit separately. Now, the Booth's algorithm gives you a uniform method of handling positive as well as negative numbers. Now, the basic idea here is, when you look at the addition from a string of ones in the multiplier, that can be converted to a single addition and a single subtraction operation. Say for example, when you have to do a 32 by 32 multiplication, because you have 32 bits in the multiplier, you have to basically form 32 partial products, and then all these partial products will have to be added using whatever addition technique that we discussed earlier. Now, instead of having 32 partial products, if you are able to reduce the number of partial products, that is going to have a reduction in the number of operations that is to be performed. So, you are trying to utilize that concept. Say for example, if you are looking at a number here, what happens is, you have a series of ones here, 5 ones, 1 1 1 1 1, and you have a 0 here and you have a 0 following that. So, whenever you have a change happening, so this sequence of ones, you have a change from 0 to 1 happening here, and you have a change from 1 to 0 happening here. So, this sequence of ones, a string of ones, can be replaced by one addition operation and one subtraction operation. So, wherever you have a change happening from 0 to 1, that is converted into a subtraction operation, and whenever you have a change from 1 to 0 happening, that can be converted into an addition operation. So, basically that is the concept of your Booth's algorithm. So, when you have a sequence of ones coming in, you can replace that by one addition and one subtraction. So, that is the basic idea. So, this is equivalent to when you have a 0 0 1 1 1 1 1 0, this is obviously equivalent to this minus this. So, we are not changing the Booth's multiplier value at all, it is just representing as, instead of writing it as 14, you are writing it as 16 minus 2. So, similarly you can do the same operations with these bits also. So, this requires addition for 5 bits, because you have 5 ones here, you will have to form the partial products for these 5 ones and you will have to add all of them. Now, in this case you just have one addition operation to be done and one subtraction operation to be done. So, you have reduced the number of operations that will have to be done. Now, this works well only when you have a sequence of ones coming like this or a sequence of zeros coming together, because you are only replacing the sequence of ones with a single addition and a single subtraction. If you have alternate ones and zeros coming in, then each of them will have to be replaced by an addition and a subtraction. So, it becomes obviously becomes a bad Booth's multiplier. So, Booth's algorithm basically works like this. So, you have, if the current bit is 1 and the bit to the right is 0, that is, you are doing a transformation from 0 to 1, you will have to do a subtraction operation. A 0 to 1 will have to do a subtraction operation. A 1 to 1, there is no change, because the previous bit is also 1, this bit is also 1. So, you do not have to do any operation. Similarly, if your previous bit is 1 and the next bit is a 0, you are doing a 1 to 0 transformation. So, that you will have to perform an addition operation, and if it is a 0 to 0, you will have to not do anything. So, that is indicated as a middle run of zeros. So, when you have a 0 to 1 transition, it marks the beginning of a run of ones. Say for example, I have a 0 0 0 here. So, this is the first indication of a transition from 0 to 1. So, that is indicated as a subtraction operation. Similarly, then you have a 1 and a 1, it is just a middle run of ones. A 1 and a 1 is again a middle run of ones. When you have a transition from 1 to 0, it indicates that you will have to perform an addition operation. And when it is a 0 0, it indicates that it is a run of zeros. So, you do not have to perform. So, as I pointed out, a sequence of ones here basically indicates that this is going to have double this value here. So, it is like adding this value and subtracting this weight here. So, whenever you have a sequence of ones or a sequence of zeros coming in, you do not have to code every multiplier bit, just look for changes happening in the multiplier bit, and it is enough if you just code them. This is the Booth's algorithm. Now, this is again a modification of the Booth's algorithm. So, Booth's algorithm is guaranteed to give you results, good results, whenever you have a good Booth's multiplier. A good Booth's multiplier is one which has a sequence of ones or zeros coming. It is definitely guaranteed to give you reduced number of partial products. Another important advantage of the Booth's multiplication technique is that it treats positive as well as negative numbers uniformly. All you have to do is, whenever a negative number is to be represented, you represented it in the 2's complement representation and perform your multiplication operation just the same way. But when you go in for the multiplier as such, whether it is a good Booth's multiplier or a bad Booth's multiplier, it depends upon the data. So, the first step that you do is, once a multiplier has been given to you, you recode it using the Booth's technique and convert it to a Booth's multiplier. Now, only when the Booth's multiplier has a number of zeros in it, it is going to be effective. So, it is basically data dependent. Now, in order to again leverage even this point, try to reduce the number of partial products, we modify the Booth's algorithm slightly, and that is called the Radix 4 modified Booth's algorithm. So, what we try to do here is, instead of just looking at 2 bits and trying to code it, we try to look at 3 bits. We try to look at 3 bits, do the encoding using Booth's multiplier, and so you have, in the case of the Booth's multiplier, if you have an original 32-bit multiplier, the Booth's multiplier also recoded multiplier will also have 32 bits. So, you will definitely have 32 partial products, but if you have a sequence of zeros and ones, the number of partial products are going to be reduced. Now, in this case, what we are trying to do is, we are going to form a 32-bit multiplier, but try to combine 2 bits together, pair up the Booth's multiplier bits, bring in the effect of these 2 bits into 1 bit position itself. So, you will not have a 32-bit multiplier at all, you will only have a multiplier which is half the size. You will have only a 16-bit multiplier. So, in any case, irrespective of the data, irrespective of whether it is a good Booth's multiplier or a bad Booth's multiplier, you will find that the number of partial products is only half. So, that idea is shown here. Say for example, I have a 0 0 0. So, these are the current bits and this is the bit to the right. So, basically what we try to do is, a 0 to 0 is coded as a 0 and 0 to 0 is coded as a 0. So, you have 2 multiplier bits 0 and 0 Booth's multiplier bits. Now, what we try to do is, we try to combine those 2 multiplier bits into 1 multiplier bit and bring it to the rightmost position. So, the recoded value is just zeros, when that is basically that will basically happen when you have a sequence of zeros. Now, when you have something like this 0 1 0, you look at a 0 to 1 transition and you look at a 1 to 0 transition. Now, a 0 to 1 transition is coded as a negative operation and a 1 to 0 operation is coded as a positive operation. So, you get a -1 for this, and this is with a place value of 2. So, this is going to have a place value of 2. So, you combine your 2 with your -1, you get a value of 1. Similarly, you can do the recoding for the other bits also. For example, when you do a 1 0 0, 0 to 0 is coded as a 0, 0 to 1 is coded as a negative transition. So, but that has a place value of 2. So, when you bring it to the other bit position, it does not just take a value of -1, it takes a value of -2. Similarly, you can find out the codings for everything. So, the Booth's original multiplier is formed first of all, and then you form the radix for modified Booth's multiplier, where it will either be a 0 or it will be a 1, it will be a 2, a -1 or a -2. So, when you actually perform the multiplication, -1 can just be taken care of by just finding out the complement of the number, -2 can be taken care of by finding out the complement of the number and shifting it left by 1 bit position. Similarly, when it is a multiplication by 2, you just have to take the product as such, it is 2 into 1. So, take the multiplicand as such and shift it left by 1 bit position, that will give you the partial product, appropriately shifted partial product. So, this is the advantage of the modified Booth's algorithm. So, the original Booth's algorithm gave you advantage only in terms of the operations, negative number operation, and the other advantage basically was data dependent. Now, with the Radix 4 modified Booth's algorithm, you get the advantage of uniformly treating negative numbers. At the same time, the partial products will definitely get reduced by half. So, to give you a summary of this, it is the same insight as 1 bit Booth's, simply adjusted for alignment of 2 bits, and it allows multiplication of 2 bits at a time, and it definitely reduces the number of operations to half of the original Booth's algorithm. Now, having looked at these multiplication techniques, how do you build a fast multiplication hardware? So, when you have to build a fast multiplication hardware, first of all, you will have to try to reduce the number of partial products you have. So, in order to reduce the partial products, you will have to look at what is the called the modified Booth's algorithm. So, modified Booth's algorithm will try to reduce the number of multiplier bits to half of the original multiplier bits, and once that has been constructed and you have constructed the partial products, you can just look at a tree of adders which will use carry save addition and do the multiplication at a faster rate. So, this basically gives you a feel of the tree of multiplication operations. So, you look at carry save addition being used here, you look at you also make use of the modified Booth's algorithm. So, all these concepts are brought together when you look at a fast multiplication hardware. So, the next operation that we look at is binary division. So, if you look at the paper and pencil method of binary division, we all know that this is the dividend, this is the divisor, and we try to find out the quotient and the remainder. So, in order to find out the quotient and the remainder, what we basically are going to do is, we know that we have to take the first bit of the dividend, check whether the divisor goes into it. If the divisor goes into it, you are going to generate a quotient bit of 1. If the divisor does not go into that dividend bit, you are going to generate a quotient bit of 0. You are going to consider the next 2 bits together. So, instead of taking just 0, you are going to take 0, 1 together, and then again check whether the divisor is greater than the dividend. You keep doing this till you successfully come across the bits which are equal to or greater than the divisor. So, at that point your quotient bit is going to become 1, then you are going to subtract the divisor from the dividend, you are going to get what is called a partial remainder. To that partial remainder, you are going to bring in the next bit, and that is how you are going to do with the paper and pencil method. The only difference in your paper and pencil method is, you do not have to systematically check, look at 0 and check whether 0 is greater than 1000 or not. By just looking at this itself, you know that you will have to, because this has 4 bits, you will have to look at 4 bits. These 4 bits are 0100. You know that 0100 is obviously smaller than this. So, you generate a quotient bit of 0, bring in the next bit and only do the subtraction operation. But when you do a machine implementation, you have to do it a little more systematically. Now, the paper and pencil method has been indicated here. So, as I told you, you look at the first 4 bits, you know that it is not going to work. So, you can't generate a quotient bit of 1. Now, you look at the first 5 bits, subtract the divisor from it, generate a quotient bit of 1, and this is the partial remainder that you get. Now, to this partial remainder you will have to bring in the next bit, again find out whether the divisor is greater than this or not. You find that the divisor is greater than this. So, you generate a quotient bit of 0, again bring in the next bit of the dividend here. So, that becomes your new partial remainder. Again check whether this partial remainder will be greater than or equal to this. So, do a subtraction operation and check. Now, by looking at it you know this is the divisor is greater. So, again generate a quotient bit of 0, bring in the next dividend bit. Now, you know that your divisor will go into your dividend, do the subtraction operation, you get a remainder. So, this is the remainder and this is the quotient. So, when you started off with this and this as the divisor and this as the dividend, you get a 4-bit quotient here and you get a 4-bit remainder. So, this is the paper and pencil method of binary division. Now, the same technique is adopted when you go in for a machine implementation of binary division. Only thing is you can't just look at something and decide whether the number is greater than or not. So, every time what we do is we have to do a trial subtraction. You subtract, find out whether it is greater than or less than, accordingly decide what your quotient bit is going to be, then bring in the next bit and keep continuing. So, if you look at the steps in the hardware, all you have to do is shift the dividend left by 1 bit position. So, you bring in the first bit of your dividend, subtract the divisor from the left half of the dividend. So, you are subtracting the divisor from the bit that you have shifted in, and if the result is positive, then you know that the divisor was equal to or less than the dividend that you considered. So, in that case you have to generate a quotient bit of 1. In case if it is not true, if the result is not positive, if the result is negative, then you will have to generate a quotient bit of 0, and you know that the trial subtraction that you did is wrong. So, you should not have subtracted the divisor because the divisor is larger than the dividend part that you considered. So, you will have to go back to the original place and start continuing your operation with the next bit. So, in order to do that, in order to repeat from the beginning, you have to restore back your original value, add back whatever value you subtracted and repeat from the beginning. So, when you repeat from the beginning, you consider the next bit and keep doing this every time, and once your result becomes positive, you generate a quotient bit of 1, and for the with the partial remainder, the subtracted value is your partial remainder. Bring in the next bit of your dividend and keep doing this depending upon the number of bits in your dividend. So, this is the binary division algorithm and this is the binary division hardware. So, you have a divisor here, you have the remainder and the quotient. This is where your initial dividend is stored, and then you store your remainder and quotient here. This is the control unit which looks at the result of your subtraction operation and decides whether to generate a quotient bit or 1 or 0. So, initially what you do is you take in the first bit of your dividend, shift your first bit of your dividend here, subtract it with the divisor, decide whether the result is positive or not. Depending upon the result being positive or not, which goes to the control unit, the control unit generates a quotient bit and restores back the original value, and then the process continues. So, this is your division hardware. If you look at the hardware, you find that there is a lot of similarity between this hardware and the multiplication hardware which we discussed earlier. So, the multiplication and division can in fact use the same hardware. So, this is the division algorithm that I discussed, and in this case, because we are restoring the partial remainder every time whenever you do an unsuccessful division operation, it is called a restoring division. If you recall the steps that we did, we taken 1 bit of the dividend and from that you subtract the divisor, and if you find that you get a negative result, you know that you should not have started with only 1 bit, you should have taken 2 bits and then do the process. Now, how do you get back the original bit? By doing a restoration operation. So, your trial subtraction was wrong. So, because of that you will have to add back whatever you subtracted, and because every time you are doing the restoration operation, it is called a restoring division technique. Now, the other technique for division is what is called the non-restoring division technique. So, in the case of the concept does not change in the case of non-restoring division. Division is always done in the same way, you have to do it in the same way. Only thing is, we are trying to optimize the algorithm slightly by trying to combine what happens in two successive steps. So, in every step what we are trying to do is, we are trying to check whether the result is positive or negative. If the result is positive, we try to generate a quotient bit of 1, and then we try to bring in the next bit of the dividend and continue our process. Do the next shift left operation to bring in the next bit of the dividend and continue. On the other hand, if the result is negative, we first of all do a restoration operation, and to that restored value, again after generating a quotient bit of 0, we again do a left shift to bring in the next bit of your dividend and continue this process. So, what we basically do is, we check the sign of the partial remainder. If the sign is negative, we shift and add. If the sign is negative, it means that it was a unsuccessful attempt. So, what we try to do is, we try to first of all add to restore back, and then try to shift and continue with the operation and generate a quotient bit of 0. If the result is positive, then what we try to do is, we do not have to do a restoration operation at all. So, you straight away go in for a shift operation, so which will give you twice the value, and then do a subtraction operation, and accordingly you will have to fix the quotient bit. So, if it is a positive result, you fix a quotient bit of 1, if it is a negative result, you fix a quotient bit of 0. And finally, if the remainder is negative, you know that you have to add the divisor. So, basically what we are trying to do in the case of a non-restoring division algorithm is, we try to combine the steps that happen in two successive operations. Instead of doing a restoring, we do a restoring operation, then do a shift left and a subtract in one case. The other case, we directly do a shift left and we do a subtract. So, these two operations are combined together, whatever we do in two successive steps are combined together, and the algorithm is given this way. So, at every step you check the partial remainder. If the partial remainder is negative, so but the first case is, you will always have to bring in the first bit of your dividend. So, first of all bring in the dividend, do a subtraction operation, and then you are going to get a positive or a negative result. So, if the result is negative, just do a shift and add and generate a quotient bit of 0. If the result is positive, do a shift, that is a left shift, and a subtract and generate a quotient bit of 1. Now, finally, when you have a negative remainder, that is the final step. Suppose if I have already carried out n division steps, I do not have another step to do. So, you are in your final step of division. So, and the final result is negative, there is no more step that you can combine, and because you do not have anything else to combine, you will have to do the restoration operation. So, if you get a negative result, finally add back the remainder, add back the divisor, so that you will get the correct remainder. So, that is the non-restoring division algorithm. So, to summarize, we have looked at binary adders initially, we looked at ripple carry adder, we looked at the carry look ahead adder and carry save adder. Now, all these concepts of carry look ahead addition and carry save addition are used in the binary multiplication algorithm that we looked at. So, in the case of binary multiplication, we initially looked at a combinational multiplier, which just makes use of combinational components alone without any sequential components. And then we moved on to a sequential multiplier, which apart from the combinational components also makes use of sequential components. So, you have registers to store the multiplier, the multiplicand and all that. You have appropriate shift operations taking place, and the algorithm makes sure that the multiplication happens. And then we looked at what is called the Booth's algorithm, which helps you optimize the multiplication process. So, in the case of optimization of the multiplication process, what we try to do is, we try to harness the fact that we have a continuous stream of ones or zeros. So, whenever you have a continuous streams of ones or zeros, it is not necessary to generate the partial products independently. All the partial products you can combine them, because a sequence of ones, say for example, if I have to multiply by a 6, which is represented by 111, if I have to multiply it by 14, which is represented by 1110, then instead of that it can be done by adding a 16 and subtracting 2, because 14 you know is going to be 16 minus 2. So, 16 is you are going to have a 1 in the next bit position and 2 is going to have a 1 in the least significant bit position. So, that way you can try to reduce the number of partial products that get generated. But again, Booth's algorithm gives you an advantage only when you have a very good Booth's multiplier, that is when you have a sequence of zeros or sequence of ones coming in, because only when you have a sequence of zeros or ones coming in, you do not have to perform any, there is no transitions happening. So, it can just be coded as zeros and ones. Whenever you have a 0 to 1 transition happening or a 1 to 0 transition happening, that will have to be encoded as either a +1 or a -1. So, in order to avoid that, harness the fact that even when the Booth's multiplier is a bad Booth's multiplier, you still get advantage of that. We looked at what is called the modified Booth's algorithm, where conceptually it is the same, only thing is we try to look at combining two Booth's multiplier bits together, and looking at the place values, you combine them into a single multiplier bit and hence reduce the number of multiplier bits to half, otherwise it is the same. Now, then we looked at what is called the fast multiplication techniques, where all the concepts that we discussed with respect to carry look ahead addition and carry save addition along with your Booth's multiplication algorithm is used when you look at the fast multiplication techniques. So, just looking at the number of multiplier bits, if you have to generate that many number of partial products, try to use Booth's multiplication, try to use the recoded Booth's multiplier, which will reduce the number of partial products, and then try to look at carry save addition, which will also help reduce the number of levels of addition that you will have to perform in order to perform your multiplication operation. Finally, we looked at what is called the binary division techniques. We looked at both restoring division technique and non-restoring division technique. So, in the case of restoring division technique, every time you perform a trial subtraction, you find that the result is negative, you will have to go back to your original state by doing a restoring operation, which is the normal pencil and paper method of operation. The only difference in your non-restoring division algorithm is that you try to combine the operations that happen in 2 successive steps. So, whatever happens in 2 successive steps, combine them together and then bring them as one step. So, the advantage of the non-restoring algorithm is that you will either have a shift and an add operation or a shift and a subtract operation in each step, whereas in the case of restoring division algorithm, you may have to do a shift, subtract and then a restore. So, the non-restoring division algorithm basically gives you improvement in terms of the number of execution steps that will have to happen. Thank you.